what we're going to start doing this week, we're actually going to go in a little bit weird of an order, and I'll kind of explain that over email. Or maybe we'll give a brief explanation now of what's going to happen over the next couple weeks. So what we have started into is trying to figure out when series converge and when they diverge. So we're looking at series convergence and divergence. And as far as our schedule, we're going to rearrange a little bit because of election day next week. But when I started to put the schedule together, I actually think I think it will go better. So I want to kind of outline what we're going to do. So far, what we have done with series is we've talked about geometric series primarily. We've also talked about splitting them up. So like sum, difference, and constant multiple. And then we've talked about telescoping series, which is kind of an aside. So what we're going to start doing is we're going to be looking at just series in general. So if you see a series, we want to be able to show whether it converges or not. In a lot of cases, we're not going to then be able to find the sum. We have been able to on geometric and telescoping. That's why we study those first. You're able to get a formula where you then can get a formula, or you can then get the exact sum. The limit as n goes to infinity. What we're going to be doing now is we're going to be looking at series where we're probably not going to know what the sum is. We're just going to know that there is a sum if it converges, and there's not obviously a sum if it diverges. So we've looked so far at this. We've also looked at the K-term test. And just kind of as a quick review, can someone summarize what the K-term test said? So like it relates a sequence and the corresponding series.
That if the limit of the series goes to 0, then it converges, or no, then it diverges.
If the limit of this, you're good. If the limit of the sequence is not 0, so like if the thing that you're adding up does not approach 0, then the series, which is the sum, has to diverge. Does that make sense to everybody? The idea is like, let's say that the sequence converges to something even really small, but not 0. If it converges like 0.1, when you add billions and billions and billions of those, that does not converge to a number. Does everybody follow that idea? That's kind of an overarching thing we're going to be using a lot. Okay, and so that's what we've kind of discussed up to this point. The stuff on the left, those are kind of the primary things we're going to be dealing with, and then we're going to add to that. So today we're going to start talking about what's called P series. And then we're going to be talking about the comparison tests. Okay, and that's going to be the topic for today. Tomorrow, my bad, today and Tuesday. Then we're going to go into what's called absolute convergence. And alternating series test. That's going to be the topic Wednesday and Thursday of this week. Then we're going to backtrack a little bit. So the stuff on the left, those are the primary ways to show whether series converge or diverge. There's 2 more that we'll add on at the end of next week. But we're going to backtrack a little bit, and we're going to do improper integrals, which was the topic that was scheduled for the week of the last exam that we postponed because I didn't want you to have to worry about it. the week of the exam. It wasn't relevant really at that point, and it is relevant for what we're going to be doing right after that. So that is going to be Monday's topic, but it won't be live. And so I'll send you guys a link to probably 2 quick videos on that you'll use for Monday instead. I can't be available. I'm out of town on Monday, and so I won't be able to do a live lecture. I'm out of town, like without internet type of out of town. So anyway, so that's a good place to put that anyway, because that'll work for a good static lecture. So you're going to do that for Monday. Tuesday's election day, so we won't have anything scheduled for Tuesday. And then the integral test is what we're going to cover next Wednesday, and we will have a live lecture for that. So this next Monday won't be live. All right, and this one will be live. And then I'll keep you posted on homework, and then we'll do the ratio and root test. And that's kind of back over here, my bad. So this is next Monday. This is next Wednesday. And then this is next Thursday. All right, and that'll kind of finish up series convergence. With the next week, you have a test, and we'll figure out, we may have to work a little bit ahead of the test before that starts, but the test will cover up until that. So third exam will cover up to and including the ratio and root test. So we'll actually get done with all the material next week, which I think is really good. Improper integrals, like I said, was technically on the schedule a couple weeks ago when we had the test, but it really fits better here anyway. And it's a good one where it doesn't really need to be live. And so you'll be able to watch a video that way. I think it'll actually make more sense after we talk about P series anyway. And so we'll kind of see how that goes. But obviously, you ask questions as you have them and stuff like that. So that's kind of an overview of what's on the next exam. So the sequences stuff before this would be, but then this is the bulk of the exam and what we really should be looking at. We're going to stick right now with written homework. So you have seen CrowdMark email you 2 assignments. So homework for this week will be series 3 and series 4. Series 3 will do problems numbers 1 through 29. And then series 4 will do problems 1 through 10. As far as where that stuff fits, series 3 is here. And then this is series 4. And so you'll have those problems to do. Those worksheets, they're on the shared drive. They're in unit 3, folder 2, and they're labeled the way they are. You can see which one's series 3, series 4. You also have worked out solutions to all those. You have to submit your own solutions on CrowdMark. They can be direct copies of mine if you want. They don't have to be unique. Obviously, you need to make sure you understand how to do the problems. I'm giving you the solutions because I think they help. But if you're just copying them over without understanding what's going on, that's going to be a real problem for the test. Does that make sense to everybody?
I was just wondering, how much of series 3 is going to be covered, like in the lecture today?
We're going to find out. You won't be able to do everything, but you'll probably have an idea. And then tomorrow we'll kind of clean that up. Tomorrow will be lots of examples. Okay. All right. Yeah. Other questions? But this will all be due next Monday. Okay. So you can kind of pace it how you want. It's all due next Monday. All right. Other questions? Yes, so far? All right. So that's kind of where we're looking for the next 2 weeks. Election day is a university holiday. I don't want you to have an assignment that corresponds to that day. So we're trying to pace it that way. I'm trying to keep Fridays as no class or study sessions if we need to, but no class on Fridays. We'll do 4 days a week. All right. So anyway, what I want to look at next is I want to talk about what we've studied so far, which is the big type of series we've studied so far is geometric. And then we have the K-term test. I should have started that up here. And then we're going to talk about P series, which we've not talked about yet. Okay, so the K-term test says that if the limit as k approaches infinity of AK is not 0. So remember that you always have, when you're talking about a series, you have the series, which is sigma notation. You're adding up a bunch of stuff, but you also have the sequence, and that the sequence is the thing you're adding. Okay, and so if the thing you're adding does not approach 0, then the corresponding series, the infinite series, AK, diverges. And so that applies to any series. If you can look at it and you know the sequence part doesn't go to 0, then automatically you know the series diverges and you're done as far as proving whether the series converges or diverges. Geometric series says that if we have the sum k equals 0 to infinity of AR to the k, that converges if the absolute value of R is less than 1, that diverges if the absolute value of R is greater than or equal to 1. And we can find the sum of that, but right now what we're working on is how to show whether something converges or diverges, not how to find its sum. So we're going to kind of get away from that. We've kind of done the ones where we're able to do that, and now we're just going to figure out, okay, does it converge or not? And so this is what determines whether or not it converges. P series is a result that, because of the way we're changing up the order, we don't have a proof of this yet. And so when you do the integral test stuff that we're talking about next week, so on next Wednesday's lecture, is that right? Yeah. Next Wednesday's lecture, we'll talk about the integral test. We're able to prove P series from the integral test. So for now, we're going to just take this as fact, and then we're going to talk about the proof of it next week. But a P series is one where you have 1 over k to a power, k to the p. Okay, so like 1 over k squared, or 1 over k to the third, or 1 over k to the 1/2, 1 over k to the first. So the harmonic series would be a P series. So if you have that, this converges if P is bigger than 1. And it diverges if P is less than or equal to 1. So if P is 1, that's the harmonic series because it's 1 over k to the first. If P is 1/2, or if P is 0.9, or if P is -1, then it's divergent. Okay, and so if P is, obviously +3 or +4 or +10, then this converges based on what we're saying. And so these two together are a real big deal because this covers all exponentials. Okay, exponentials meaning you have x, normally a number to the x. In this case, it's a number to the k. Does that make sense? So if you have a number raised to the k power, that's a geometric series, and that covers all exponentials. Well, this covers all power functions, which is why it's called a P series. And they're not exactly power functions, like it should be x probably, but you think of it that way. So the expression is k to a power. So if you have k to the 5th, that's the same thing. Like if I were to dealing with k to the 5th power, that's the same thing as 1 over k to the -5th. So it's a P series. Does that make sense? And so then that diverges because -5 is less than 1. And you also could say this diverges because of the K-term test. But these two together cover basically any simple series where you have a number to the k, or if you have a k to a number. So all exponential functions covered here, all power functions covered here. So we're going to do several where I just want to kind of drill that. And so the directions for pretty much all the problems today, directions are going to be show whether the series converges or diverges. But this time, if it converges, we're not going to bother finding its sum. Sometimes we can. but we're just going to say whether it converges or diverges. So all right, so I want to look at these two together, and then I'll probably just put a bunch on the screen and let you guys do them. So if it's an exponential, like the first one is, it's geometric, or you can write it in the form where it's definitely geometric. And so when we do this problem, so I'll do our work in blue. When we do this problem, we're going to rewrite this as the sum k equals 1 to infinity of 1/3 to the k. Does that make sense to everybody? And we could do that because 1 to the k is the same as just 1. So 1/3 to the k is the same thing as 1/3 to the k. And so now that's geometric. It's in this form up here. And so we say, okay, well, then this converges. Our rationale is that it's geometric. The absolute value of r is 1/3. And what's significant about that is that that's less than 1, and we're done. Does that make sense to everybody? Any question? All right. And so then, okay, on the second one, we've got 1/k to the 3rd power. Well, that's a p series because it's in this form. So we say, okay, well, this one converges too. It's a p series where p is equal to 3, which is bigger than 1. And that's the rationale. So we have it converges if p is bigger than 1, it diverges if p is less than or equal to 1. And those two are real simple. And like I said, the proof of p series is something we're actually going to do next week when we deal with the integral test. We're going to prove why this is the case. But for now, we're going to accept it as fact that that's the case. And so once you have it in that form, you're done. Any questions on those? Is that pretty easy so far? All right. Okay, so I'm going to put some more up, and I want you guys to just work through them quickly. So, so number 3 is going to be the sum k equals 2 to infinity of 4. All right, so I'm going to give you maybe a minute or two to try these 4 problems, but go through, write up, they're quick proofs, but do write out the proof and write out the explanation, figure out whether they converge or diverge, and give an explanation as to why. And then we'll check them together here in about a minute or two. All right, so let's start working these. So the first problem, we can rewrite this way. We can say, okay, that's the sum k equals 2 to infinity. And very neat. Of 5 times 1/4 to the k. And then that then converges. Because it's a geometric series, the absolute value of r is 1/4, which is less than 1. On problem 4, I guess maybe I should have done an example like this with you beforehand, but you can factor the 5 out as a constant multiple. And so it's 5. It's almost like what we did with integrals, where we would kind of factor out constant multiples like that. And so the idea we discussed last week is that, okay, if this series converges, then that means it goes to a finite number. And so 5 times it would also go to a finite number. If this diverges, then maybe it goes to infinity. Well, 5 times that would still go to infinity. If it goes to negative infinity, it still goes to negative infinity. And if it bounces between two values, then it's going to bounce between two values 5 times that. And so if this converges 5 times, it still converges. If this diverges 5 times, it still diverges. And so technically here, what we would say is we say, okay, it does converge. And it's not just a p series, it's a constant multiple of a p series. And so I would get, if you didn't put that, but you would say, okay, it's a constant multiple of a p series where p is 4, which is greater than 1. And if you didn't say constant multiple, because we had not discussed that with the p series today, that would be okay. But technically we should be saying that. And so maybe insert that in your proof. But do we at least get that was converging? Did you guys get that? Okay. All right. And so then, okay, the next one, 1 over k square root of k, you can rewrite as 1 over k to the 1/2. That diverges because it's a p series where p is less than 1. So p is 1/2. And what's significant about that is that it's less than 1. And then remember on these problems, like, especially when we get into the ones later today and tomorrow, what you're writing is not really much work to find an answer. It's work to prove that you're right about your answer. So like, I think we can all look at this and think, okay, well, it's 1/2. And so p is 1/2, that's less than 1. You don't need to write that in order to figure it out. Remember, you're doing a proof. You're providing an explanation. You're not trying to determine an answer by writing that stuff out. All right, any questions so far? You guys good? All right, and so then on number 6, you have to do just a slight manipulation. You rewrite it as 1/3 times 5/3 to the k. K equals 1 to infinity. And then that's going to diverge because it's geometric. The absolute value of r is 5/3, which is bigger than 1. So it diverges. As far as the constant multiple thing, you technically don't need to say that here, because just because the form we write geometric series in has a constant a in front of it, the p series does not. And so that's why, to technically match what we've got, we should be saying constant multiple here, but we don't need to here. All right, any questions on those 4? Is everybody good? Can't see very many people today, so if you do have a question, definitely. Oh, how do you split up 6? Oh, okay, because 3 to the k plus 1 is the same thing as 3 to the first times 3 to the k. So the question is, how did I split up 6? And that's what I did down here. So then I got it as 5 to the k over 3 to the k plus 1 equals 5 over, or 5 to the k over 3 to the first times 3 to the k, and then went to what I have. Does that answer the question? Does that make sense? Okay, cool. Any other questions so far? Okay. Okay, so what's going to happen is with almost all of the problems, so all the stuff I'm listing up here, this comparison test, all this series 3, there's like 30 problems on that. Most of them are more complicated than what we just did. Series 4, they're all more complicated than what we just did. But what's going to happen in almost every case is they're going to boil down to one of these two types. They're going to boil down to geometric or P series. And so like when we look at the next problem, and it's going to be a few minutes before we actually solve this problem, but if we look at this problem, let's say k minus 6 over k to the third plus 5k minus 2 from k equals 1 to infinity. So if we look at that, that's a lot more complicated looking than the other ones we've done. But remember that we're looking at the infinite sum, meaning k is going to infinity. And so we talked a lot about sequences for that. And so like, again, we're not going to start working this problem yet, but if you think about what we thought about with sequences, what's relevant on this as k goes to infinity? Like what's actually relevant on top when k goes to infinity? The k, the 6, both of them, or what?
Just k.
Really just k. And then on the bottom, what really matters?
K to the third.
K to the third. So what you should be thinking, and not necessarily what you should be writing, is really as k goes to infinity, it's pretty much that. But what is that? What's that simplify to?
1 over k squared.
Yeah, and what's 1 over k squared? What type of series is that?
Power.
It's a power series or P series. And so this converges. Does that make sense to everybody? So, okay, on all these problems, until we get to alternating ones, but on all these so far, if this converges, so does this. Does that make sense? So like one thing I was saying a couple times last week, and I'm going to emphasize over and over again, is you're going to know the answer to these problems before you really write anything. Like you might jot that down, but I think most of you could look at that and say, okay, k over k to the third is the same as 1 over k squared. Well, 1 over k squared converges, so then this one does too. Now, they do not converge to the same thing because of this other stuff, but they do both converge. Does that make sense to everybody? Now, we have not proven that. We need to talk about methods in order to do that, but it is always the case that if it's a normal type of problem like this, and I'll define more accurately what I mean by normal type of problem, but if it is a normal type of problem where it's all power functions over all power functions, it's just going to do whatever this does. If this converges, this converges. If this diverges, this diverges. Now, they do not necessarily converge to the same number. In fact, they almost for sure do not. But if this converges, then this still converges. Does that make sense to everybody, that thought process? Okay, so we're going to prove in a few minutes that this converges, but I want to talk about how to think about that first, or how to go about it. So what we're going to look at is series with all positive terms. Okay, so series where what you're adding is all positive. Now, I want to think about a series then, AK. And so everything in the thing that you're adding up, every term in AK, that's a positive number. So if you add all those up and it converges, then it converges to a positive number. Does that make sense to everybody? So there's no way it like converges to a negative number. There's no way if you're adding positives that it converges to 0. If you add positives, it's going to converge, the sum is going to converge to a positive number. Does everybody get that idea? Everybody clear? Okay. Now, what if it diverges? How, in general, can series diverge? So there's 3 kind of ways we think about series diverging. What's the easiest way for series to diverge? If you add up an infinite number of numbers, logically, what's that probably do anyway?
Infinity.
It goes to infinity. So the most obvious way for a series to diverge is go to infinity. What's the next most obvious way for a series to diverge? Do you think?
Alternating.
Okay, I would say negative infinity, but it could also alternate. Okay, so and next most obvious, that's a subjective thing. So if you, anyway, negative infinity could go to negative infinity, could bounce like 3, 5, 3, 5. So if you're adding numbers, you get that where it bounces between two things. And maybe weirder patterns could happen. But like those are 3 common ways for series to diverge. Does that make sense to everybody? We clear? Okay, now, if you're adding all positive terms, can it diverge by going to infinity? So if it's all positive, can this happen?
Yeah.
Of course. So if you add a bunch of positive numbers until you think more about it, probably it does go to negative infinity, right? And so, okay, so yes, that could happen. Could it go to negative infinity? No chance. If you add positive numbers and you somehow get negative infinity, you're doing it wrong, right? If you add positive numbers, you get positive answers. Everybody clear? Now, could this happen? 3 and 5 and 3 and 5, those are all positive. But if the series that you're adding up, if everything that you're adding is all positive, can you bounce from 3 to 5, 3 to 5?
No.
No, why not?
Because to go from 5 to 3, you're doing less.
To go from 5 to 3, you've gone down, which means you had to add a negative number. So you cannot bounce between two values. Now, the terms you're adding could, but the sums, the partial sums, cannot if what you're adding is positive. So if it's all positive terms, that can't happen either. Does everybody get that? That's a weird distinction. The things you're adding are all positive. They could bounce between two numbers, but the sums cannot. Because like to go from 3 to 5, you do +2, that's fine. But to go from 5 to 3, you have to add -2. That's not possible if it has all positive terms. Does that make sense? Okay, so the idea behind what we're about to do for more complicated problems like this is if it's a series that has all positive terms, the only way for it to diverge is for it to go to infinity. Does that make sense? So if you add all positive numbers, the only way that can diverge is if it goes to infinity. Now, in general, that's not true, but when they're all positive, that is true. Does that make sense? Okay, so it either, for series with all positive terms, it either converges or it diverges because it goes to infinity, not because it does one of these things. Okay, so then what if I can prove? So I'm going to have an easier series. And you know what? We're going to write that in green. And the easy series is going to be like when you have this complicated one, the easy series is going to be this easy one that you're coming up with by looking at the biggest stuff. Does that make sense? So we have this series that's hard, and then we have this series that's easy. The easy series on most problems is going to be a P series or a geometric one. Does that make sense? Everybody clear? Okay. It's going to be a series that has all positive terms like this, or for large N, it's going to be all positive. All right. And so if the easy series converges, then we can think of it graphically as doing this if it converges. Now, it's a bunch of separate dots, so it's not really a smooth curve, but it's easy to think about it like this. It's going up always, right? It always goes up, but it levels off. If you're adding positives, it has to continually go up forever. It cannot be completely flat, but it can level off. Does that make sense? And in fact, AK would have to approach 0 if this converges because of the K-term test. And so the thing you're adding, it is positive, but it's incredibly small. So it would level off if it converges. Does that make sense? Everybody clear? Okay, so then what if I could prove the hard one? What if I could prove that the hard one was smaller than that? Like if I knew the hard one was smaller, is that helpful? So like if it's always underneath that, what do you know about it?
To converge to.
It has to converge to. Why would it have to converge to? If it's smaller than this one. What can it not do if it's smaller than this one?
Go above it.
It can't go above it, which means it cannot possibly go to infinity. Could it go to negative infinity if it was smaller than this? Yeah, but not if it's all positive. That's not possible ever. Does that make sense? Could it bounce like this forever?
No.
It could in general, but not if you're adding all positive terms. Does that make sense? So then, okay, it can't go to negative infinity because it's all positive. It can't bounce because it's all positive. It could go to infinity being all positive, but if it's underneath this, it can't go to infinity. So then it has to converge too. Maybe not the same thing. Maybe it converges down here, but it has to converge because it can't do the only thing that would allow it to diverge. Does that make sense? Okay, so if the harder series, if the easy series converges, so if the easy series converges and the harder series is smaller, then they both converge. What if the harder series is bigger? So like, what if it's always up here? Could it diverge then? Sure, it could go to infinity and be bigger than that. Does it have to diverge if it's bigger than that? What do you guys think? Does it have to diverge
No.
if it's bigger? No, because it could level off somewhere else. So if the harder one's bigger than this easy one and the easy one converges, that's not helpful. Maybe that's the case, but it's not helpful. Does that make sense? Okay, now, what if the easy series diverges? Oh. Nah, that's not what I'll do it. Now it is. All right. So what if the easy series diverges? And it's all positive. Then now the graph looks like that. Does that make sense? Because the only way, if it's all positive, for it to diverge is to go to infinity. Everybody clear? Okay, so now, if the harder one is bigger, or if the harder one is smaller, which one is useful in making a conclusion about the harder series?
If it's bigger.
If it's bigger. If it's bigger, it has to go to infinity too. But if it's smaller, it could go to infinity still, just slower, right? If we're down here, it could go to infinity, but slower, or it could level off. And so we don't know. So if the easy one diverges, then the useful information would be if the harder one is bigger, then it diverges. Otherwise, we don't know based on that what happens. Does that make sense to everybody? All right, now this is a really good way to think about what's going on. And if you want to see it written formally, I'll have some handouts that show that. But I think that's harder sometimes than to be able to think it through. I'd think through in a picture. So I want to go to this problem. And I'm going to write our solution in blue. And even though I do want you to think this, I'm going to erase this for now because I want to start it as though it's a brand new problem. So if you come across this problem and you're asked, prove or show whether the series converges or diverges, the first thing you should realize about this series is that for large K, all the terms are positive. How do I know that for large K, all the terms are positive? For large K, what's the biggest thing on top? K or 6?
Okay.
Okay.
K. And so for large K, K is positive. It's going to be bigger than 6. So actually it's negative for 1, 2, 3, 4, and 5. But for large K, it's positive on top. Does that make sense? And then on the bottom, the biggest term is K to the third. So for large K, this is all positive terms. All of these arguments work, even if all means large K. Does that make sense? Okay, so those arguments all work still if it's all for large K. So, okay, so then as soon as that happens, if it's all the same function type, that's what I mean by normal problems. So all power functions, K to the third, K to the first, no K. K to the first, no K. Those are power functions. If they're all power functions, or if they're all exponential functions, then you say, okay, we are going to compare this. And so what I'm writing in blue is what you write as part of the problem. We're going to compare this to the sum K over K to the third, the biggest thing on top and the biggest thing on bottom. Not necessarily the first thing, but the biggest thing. Does that make sense? We're going to then figure out what this series does. So we simplify it. It's 1 over K squared. What does that do? Does that series over here converge or diverge?
Converge.
It converges. It converges because it's a P series. So we say that. We say this one converges. It's a P series where P is 2. And what's significant about that is that it's bigger than 1. Now, what I'm writing in blue, you write as part of the solution. What I'm writing in red, you think, but you don't necessarily need to write. That means graphically, this easier series does that. Does that make sense? So then for our logic that we were talking about a minute ago to work, would we like the original series to be smaller than this one, or would we like it to be larger than this one?
Smaller.
We want it to be smaller. Is it smaller? So yes, and this is weird to think through, so everybody kind of look at the two fractions for a second. We know that a fraction is smaller if everything's positive. A smaller fraction is one that has a smaller numerator and or a bigger denominator Does that make sense? So like if we think back to fractions from like elementary school, 3 over 8 is less than 5 over 8. And you know, it's because eighths means you take a whole into 8 equal pieces. Well, you have 3 of them here and 5 of them here. Does that make sense? Okay, now, if you have the same numerator, if I have 3 over 4 versus 3 over 8, well, 3/4 is bigger because 3/4 means you're splitting a big pizza into 4 pieces and you get 3 of them. Here you're splitting the same pizza into 8 pieces and you get 3 of those. Well, you get more pizza this way. Does that make sense? I know that's very elementary and that's easy to think about here. That's harder to think about here. So you have to keep that straight. So smaller numerator, smaller fraction, bigger numerator, smaller fraction. I'm sorry, bigger denominator, smaller fraction. Make sense? Okay, let me say that again so it's actually right. Smaller numerator is a smaller fraction. Larger denominator is a smaller fraction. Does that make sense? Okay, so we're going to prove that that's the case here. We're going to say, okay, well, k minus 6 over k to the third plus 5k minus 2 is less than k over k to the third plus 5k minus 2. We're not done, but how do I know that that inequality is true? What's the only difference between these two fractions?
The numerators.
Yeah, the numerator. And this one has a smaller numerator. Same denominator, smaller numerator. So this is a smaller fraction. Does that make sense? Now, we can compare that to this fraction. All right. And so if I look at the second fraction to the third fraction, the only difference between those is the denominators. Well, this denominator is larger than that one because we add 5k to the k to the third. Does that make sense? The -2 doesn't matter because 5k is bigger than -2. And even if this was like -200,000, for large k, this would be true because 5k will eventually be larger than the -200,000. Does that make sense? Everybody clear? Okay, so this compound inequality is showing that this fraction, which is the original series, is smaller than this fraction, which is this easy series. Does that make sense? Now, graphically, that means it has to stay underneath this, but why can't it like go to negative infinity? Why is that not possible?
Because they're all positive numbers.
Because they're all positive, but that is a key part of the logic that we have said out loud, but have not yet written. Does that make sense? Okay, so for this to all work, this has all got to be positive. So we know that's true. We've been saying it. We thought about it already, but we need to say that as part of our proof. So we're going to say, okay, well, 0 is smaller than the smallest one. 0 is smaller than this, which in turn is smaller than this. Now the logic is sound. So then the original series, whoops, the sum k equals 1 to infinity of k minus 6 over k to the third plus 5k minus 2 converges by, and we're going to call this the direct comparison test, or by direct comparison. Questions on any of what we're writing? Okay, so everything that's there is a necessary part of the proof. Remember that 10 minutes ago, before we started talking about any of this, we already knew the answer. So the weird thing, and I will say this again and again, the weird thing about series problems is you are not doing all this work to determine the answer. You should know the answer before you start the problem. And your work is to prove that you are correct. It's not like normal math. Normal math, you do work in order to come up with what the answer is. Here you don't. As soon as you see this is 1 over k squared, you know the answer already. Does that make sense? And I know that's weird. Is everybody good so far? Okay, so let's try another one. Good question. So Alyssa said, how would this be asked on a test? The directions would say show whether the series converges or diverges. And that'd be it. It might say prove, same thing. So if it says that, this is what you would be expected to do. Okay. Likely that you're going to have to do a written portion of the test this time. We'll talk about that later. I don't know. I'm not sure. Yeah. Got to work that out still. All right. Other questions? Yeah, the question in chat, my bad, it's coming to me privately. I thought it was going to everybody. Sorry. I think I had it turned off. Yeah, so the question in chat, how would this be asked on a test? And then my answer is, this is what it would say. And then does that mean the test will be a crowd mark? Probably part of it, but I honestly don't know. That's going to be 2.5 weeks from now, 3 weeks from now, something like that. And so I'm working on that. All right. Any other questions so far? In a normal semester, when we had handwritten tests, you know, you just have a test and you have a bunch of these where you have to show your work. You have to show your proof. All right. So number 8, k equals All right, so let's talk about this one, and we're gonna make that K then. All right. So immediately we're gonna go to, this is a series that has all positive terms. There's gonna be some other stuff to maybe check later, but it has all positive terms, and it's all the same function type. So this is all K to a power. So our immediate thought should be, we're gonna compare to the sum 5K over 2K squared, because those are the biggest things on the top and the bottom. Does that make sense to everybody? We're going to then simplify that by factoring the coefficient out and writing it that way. And now this is the stage at which we should know the answer. So like, I think we can probably all look at this and figure out that we were going to get to this anyway, or you'll get good at that as you do this. But K over K squared is 1 over K. The sum 1 over K diverges because that's the harmonic series, or you could say because it's a P series. Does that make sense? So this diverges, meaning this original is also going to diverge. So we know now the answer. Everybody clear so far? Now we've got to do a lot of work to prove it, but that's what we now do. So, okay, so we're going to continue over here and we're going to say, okay, this diverges. And the reason it diverges is because it's a constant multiple of the harmonic series, which we talked about last week. Or you could say a P series where P is 1. Okay, so we do that part first. Now, the original is also going to diverge, but let's see if we can use the direct comparison test. So the thought process is, okay, this, it's all positive, so it goes to infinity. So to use the direct comparison test is the formal name for this thought process up here. Okay, so to use the direct comparison test, what do we want? Do we want the original to be bigger than this, or do we want the original to be smaller than this? To use direct comparison, we want it to be bigger. Is it bigger? So comparing, it is, because comparing the numerators, the numerator here is bigger numerator is a bigger fraction, and comparing the denominators, the denominator here is smaller denominator, also bigger fraction. Does that make sense to everybody?
So are you talking about like the plus and the minus signs, not the actual?
Right. So I'm saying that 5K, yeah. Okay, so two questions. One is, what am I talking about? Like the plus and the minus. So I'm talking about, okay, 5K here versus 5K here. The numerator is the same, except that this one is plus 6. So the numerator of this fraction is bigger than the numerator of this fraction. I'm then talking about, okay, 2K squared versus 2K squared. Those are basically the same, except that this one you're subtracting K. So then this denominator is smaller than this denominator. Does that make sense? Does that answer your question?
Yeah.
Okay. So overall, this is a bigger fraction because both of those behave the way we want. If they did not behave that way, we would then use a different test. So like if this was plus K, we would not know for sure that this is bigger than this. So we would do something else. It would still diverge, but we'd do something other than what we're doing right now. Does that make sense to everybody? Okay, and then a question in the chat is, why do we want it bigger? The reason we want it bigger is because this one diverges, which if everything's positive, which everything here is positive, then when it diverges, it must go to infinity. So what we would like is to be able to prove the original, the easier or the harder one, the original is bigger than that, because if it's bigger, it has to go to infinity. If it's smaller, it could go to infinity, but it could also level off. So if it's like down here, it could go way up, or it could just level off. And so we don't know. So if it's bigger, we know it diverges. The opposite was true up here. When this converged, we wanted the original to be smaller because being smaller than that forced it. It's not that we want it to diverge, it's that we know it diverges. And so this is what's going to prove that. If we can prove it's bigger, we know it diverges. If we cannot, we will use a different test later. Up here, once this easy one converges, we know this one converges, and it's easier to prove if it's smaller than that because it doesn't go to infinity. Does that make sense? Does that answer the question in chat? And does that make sense to everybody? That's a big, big concept, and it's a confusing concept. Okay. All right. And so then we want it to be bigger. It is bigger. What that then means is that we can use the direct comparison test. So I'm going to prove that this is bigger. So we've said it out loud. So I'm going to say, okay, this is bigger than 5k over 2k squared minus k. We know that's true because the denominators are the same, but this numerator is bigger than this one. So this is a bigger fraction than this. And in turn, that's bigger than 5k over 2k squared because the numerators are the same and this denominator is smaller than this one, meaning this fraction is bigger than this one. Does that make sense? Now, for all this logic to work, everything has to be positive. So if we didn't know it was positive, maybe this went to negative infinity, and so being bigger doesn't help. And so we say that it's positive, and the easiest way to do that is just say, okay, well, the smaller one is bigger than 0, which means the bigger one was too. So for all of our logic to work, everything's got to be positive. That we kind of said at the beginning, but we didn't write it down. And so we're writing that as part of our proof. Now we've got everything I've written in blue is the correct logic to prove the original series diverges by direct comparison. Does that make sense to everybody? Please ask questions if you have them, because I know this is confusing, and you'll get better at it, but there are parts of this that remain confusing. So ask, and if you feel like somebody's already asked the same question, that's fine. That happens with this. Questions? Questions on either of these? Like why they worked a little differently from each other. The same general idea, but okay. All right, so then we're going to do another one. Where are we on? Number 8, number 9. All right, so we'll come down here and do number 9. All right. Okay, so if we look at that, we're going to look at that and say, okay, well, everything's positive. They're all the same function types, so everything's a power function there. So we're going to immediately compare this to 5k to the 4th over 3k to the 6th. So we're going to say, okay, compare to the sum 5k to the 4th over 3k to the 6th. Well, that's the same thing as 5/3 times the sum 1 over k squared. That does what? Converge or diverge?
Converges.
Yeah, that converges. That means the original is also going to converge. And this is the stage where we know the answer already. But the reason this converges is because it's a constant multiple. Man. Spell things right. Constant multiple of a P series where P is 2, which is bigger than 1. Does that make sense? Now, graphically, we can think of that as meaning, well, since it's all positive, if it converges, it continues to go up, but it levels off. So we would like the original to be what? We want the original to be bigger than that or smaller than that?
You want it to be small.
We want it to be smaller. Based on the numerator, it is smaller because the first term is the same. The next largest term is negative. So this is a smaller numerator, but based on the denominator, this is a bigger fraction. It has a smaller denominator. So it would be very difficult or probably impossible, because probably not. It would be difficult or impossible to prove this is smaller than this. It's probably not smaller than that because the bottom is smaller. Does that everybody see what I'm saying? Okay. When that happens, that means the direct comparison test does not work. Instead, we use what's called the limit comparison test. It still does the same thing. It's not going to change the answer. If this converges, this still converges. Just the way you show that is different. So you say, okay, the limit comparison test says that if AK is greater than 0, BK is greater than 0, and the limit as K approaches infinity of AK divided by BK is some number that is positive. Okay, and I want to talk about what all we're saying, but I want you guys to get a chance to write that down if you want. Then the sum AK and the sum BK either both converge or both diverge, meaning they do the same thing. They don't converge to the same number, but they both converge. Maybe they diverge here. They would both diverge because they go to infinity. But okay, so you're saying AK is positive, BK is positive. The limit of one of them divided by the other is some number, and that number is positive. And so we'll talk about why this is true in a second, but because we're a little short on time, I want to get through this example, and we'll talk a lot more about this tomorrow. But what we're going to do when this relationship doesn't hold, so we want the original to be smaller, it's not. So then, okay, AK is one of them, and BK is the other one. It doesn't matter which is which. Usually I say, okay, AK is the original. So, okay, so we're going to say AK and BK are positive. So we're going to say, okay, well, 5K to the 4th minus K plus 1 over 3K to the 6th minus K to the 5th minus 2 is bigger than 0. And we're assuming for large K. And the easier one, 5K to the 4th over 3K to the 6th is bigger than 0. So this is bigger than 0. This is bigger than 0. That's 2 of the conditions, right? So AK bigger than 0, BK bigger than 0. And now we need the limit of one of them divided by the other one. So the limit of AK divided by BK. Well, AK divided by BK is the same as the original times the reciprocal of the easier one, the BK. Does that make sense to everybody? Now that limit, as k goes to infinity, where would I get this step? Where would I get that?
Just multiplying them by the biggest terms.
Yeah, multiplying the biggest term on top in the first fraction times the biggest term on top in the other fraction. Same thing on bottom. Does everybody see that? And now that limit is pretty clearly 1. Okay, looking back at this, the two series or the two expressions have to be positive, and the limit needs to be a number L, and that number needs to be positive. Well, okay, that's the number L, and that we know is greater than 0. It's going to be positive, but if you did this wrong, it might be 0 or it might be infinity. And in those cases, you cannot always make a conclusion. Sometimes you can, and we can talk about those special cases tomorrow. But if it's a finite number, you can make a conclusion. On the normal problems, it's going to be 1. And so then, okay, they both do the same thing. So the original series converges. Remember, we did that top right stuff first. It converges by the limit comparison test. And I'm going to abbreviate that LCT just because of time, but limit comparison test. Does that make sense to everybody? Okay, now, because we're almost out of time, I want to talk about the homework. We're going to do more examples tomorrow. I want to talk about why the limit comparison test works. And then I want to talk about why it doesn't really matter which one you use in a lot of cases. And so we'll talk more about that tomorrow. But I would like you to try a couple problems before tomorrow's class. So let me show you this real quick. We're going to run over just a minute. And if you need to go, of course, that's completely fine. Let's show you two things. Let's show you first this. Man, if Adobe didn't crash. I think it did. Oh, no, there it is. Maybe. Can you guys see that or no? You're not seeing anything? Okay, good.
No.
Let me try one more thing. And if not, I'll just tell you some problems to try and we'll get. Man, it's messing up. Okay, never mind. I'll show you what I was going to show you tomorrow. But if you can tonight to kind of prepare to tomorrow, if you look at series 3, which I was trying to show you on screen, the first 6 are just like basic P series and geometric, like the ones we were doing at the beginning. So, you know, you can do those very, very quickly. What I would like you to do is try problems 7 and 8, just 7 and 8, just to kind of go through a direct comparison and a limit comparison, just to kind of do that once on your own before tomorrow. We'll do a bunch more examples tomorrow. We'll talk about why this stuff works more. But somebody was asking how far would we get on series 3. Technically, we're kind of done. I mean, you definitely need more practice and we should be talking about it more, but there's not going to be any more theory. We're just going to try to clean things up tomorrow with this. So we've kind of covered most of it, but I want to talk about how to tell what to do when, and then what happens when there are minor changes. And so we'll see a lot more of that tomorrow. I think it'll make more sense, but it will help you if you've practiced one of each type, one direct comparison and one limit comparison. That's problems 7 and 8 from series 3. So the first 6 are the real straightforward ones. Try to get 7 and 8 done. Use the solutions to help you, and then we'll work more stuff tomorrow. All right, thanks you guys. Sorry I wasn't able to share the screen. Something's up with Zoom right now, but I will see you guys tomorrow. If you have questions, stick around for a few minutes. I'm happy to answer them.